Hello, this is Dr. Armand bringing you another exciting lecture in general chemistry. Today we'll be talking about entropy and free energy. Entropy is a measure of disorder in a system. Free energy determines the spontaneity of a system. So for example, entropy, when you spill a cup of water, you've increased entropy because disorder has increased because now the water is spread further apart. So second law of thermodynamics states that everything in the universe tends to disorder. And free energy determines spontaneity. So when you calculate free energy, you'll know if particular reaction or process is spontaneous, means it happens on its own accord at a particular temperature of the system. So for example, if I take an ice cream cone and sit outside and eat my ice cream, the ice cream will spontaneously melt while I'm eating it because of the heat from the sun. And so those are the two topics we'll be talking about in this lecture. So sit back, relax, and let the chemistry flow, I guess. Yeah. So chapter 20 again deals with free energy and entropy. Just to kind of give you an introduction, entropy is a measure of disorder. And as we'll learn about in a little bit, the second law of thermodynamics pretty much says everything in the universe tends to disorder. So it takes energy to keep things order. So for example, if you spill a cup of water, that increases entropy because there's more disorder. And it takes energy to go back. So it takes energy to put the water back in the cup. So that's one thing we'll be talking about in this lecture, entropy. The other one is free energy. So is a process, reaction or process spontaneous? So free energy is the difference between enthalpy and entropy. So for example, the one I used was eating an ice cream cone. Outside, the ice cream will spontaneously start to melt. So those are the two topics we'll be talking about in this chapter, entropy and free energy. So what is a spontaneous change? A spontaneous change occurs under specific conditions. This could be temperature or pressure, something like that, without continuous input of energy from outside the system. So depending on what your system is, it spontaneously occurs. For example, if you take out a few ice cubes, put them in a cup, leave them on the counter, it will spontaneously start to melt at room temperature. Under these conditions, yes, it will spontaneously melt. Now, if it's spontaneous in one direction, it's going to be non-spontaneous in the reverse direction. So to go from liquid water to ice at room temperature is going to be non-spontaneous. It's going to take energy to change it. But this doesn't mean instantaneous. This means it's spontaneous. It happens on its own accord, but it doesn't mean it happens fast. And you may wonder why, well, what about delta H? Can delta H predict spontaneous change? And the discussion here is that, we have endo and exothermic processes, and some spontaneous processes which have a delta H negative, which are exothermic, they're spontaneous. So delta H less than 0 is exothermic. So for example, at 0 degrees Celsius, water will spontaneously freeze into ice. And this is an exothermic process. Methane will spontaneously combust with oxygen. It's an exothermic process. So there are exothermic processes that are spontaneous. Likewise, there are endothermic processes that are also spontaneous. So for example, when you dissolve sodium chloride in water, you spontaneously dissolve sodium chloride into its ions. It's endothermic. And most group 1 salts, when you dissolve them, they're endothermic processes. So you have an endothermic process, but it spontaneously dissolves. So you put rubidium chlorate in water, it will spontaneously dissolve into water. And these are endothermic processes. At 0 degrees Celsius, ice will melt into liquid water. So delta H is not a good predictor of spontaneity because both endo and exothermic reactions are spontaneous. So there has to be something else we can look at to determine spontaneity. And that is entropy, which is molecular randomness, or what I like to call disorder. Entropy can be referred to as disorder of a system. And again, system is what you define. One thing to note is that this disorder, the units are joules per mole Kelvin. And the more randomness, the more disorder you have, the more positive delta S is. So when delta S is negative, means it's less disorder. When delta S is positive, it means more disorder. And so what we're talking about here is we're talking about less freedom of particle motion to more freedom of particle motion. So for example, when you go from a solid to a liquid, the movement of the particles has more freedom. So when you go from a solid to a liquid, you increase entropy. When you go from a liquid to a gas, again, you increase entropy because now the particles have more motion of movement, the energy gets dispersed. So that's why entropy increases when you go from a solid to a liquid to a gas, because A, there's more particle motion, and B, the energy is more dispersed. So that increases the randomness. So delta S would be positive. These are what phase changes. So again, solid to liquid to gas, you're increasing entropy as you go that way. Now, dissolving a salt, you start with a crystalline solid and a liquid, and you get an aqueous solution or ions in solution. Again, this increases entropy because, again, you have more movement of particles, the energy is spread out. So when you dissolve a salt in water, you form an aqueous solution, ions in solution, therefore more disorder. A chemical change, for example, if you take a crystalline solid and you form gases or ions in solutions, this increases entropy. So if you see on one side of the reaction there's no gas, and on the other side of the reaction you produce a gas, that's a clear sign that entropy has increased, because gases, they have more freedom of movement, their energy is more dispersed, so you can be sure that the entropy increased in that system. And the way we find the delta S of a reaction, of a system, or a reaction, is we take the final minus the initial, just like we did with enthalpy. And so delta S of reaction is the entropy of products minus the entropy of reactants. And this is typically found in a thermodynamic table in the back of any general chemistry textbook. And these are called molar entropies that we'll talk about in a little bit. I believe it's the second column or the third column in the table. But what you got to remember is that this is in joule per mole Kelvin. And you'll see why that's important in just a little bit when we do calculations. So for example, when we go from fewer moles of gas to more moles of gas, say from reactants to products, this increases entropy. When we go from a solid to an aqueous, say you want to dissolve a salt in water, this increases in entropy. When you want to go from a solid to a liquid, say you want to melt ice at 0 degrees Celsius, this increases the system in entropy. When you want to vaporize water at 100 degrees Celsius to gas, steam, this is a positive delta S. So what you're doing in all these final states is you're causing the particles to have more movement. The energy is more spread out, therefore entropy increases. So now I'm going to tell you some characteristics of different types of systems so you can kind of gauge, which systems will you see an increase in entropy, when will you not. And so please pay very close attention because there are exceptions, and 9 times out of 10 students will forget the exceptions, which is a bad thing because then these exceptions are going to be on the test. So make sure you remember these exceptions. So the first system we're going to talk about is dissolving a solid or a liquid in water. So we want to take a solute, put it in water, and the general rule is entropy increases when a solid or a liquid solute dissolves in a solvent. For water, it depends on the nature of the solute and the solvent interactions. For example, water is a polar molecule. If you dissolve a polar molecule in water, you're going to increase the entropy. Now, if it's a nonpolar molecule like hexane, it's not going to be miscible. So now if we talk about ionic solutes, remember ions have much more freedom of motion. And so the entropy of ions themselves is greater in the solution. So when you dissolve certain compounds in water, like sodium chloride, lithium fluoride, calcium chloride, these ions have much more freedom of movement, therefore the entropy increases. However, there are exceptions, and please remember this exception. You will see it on the exam, this exception right here. Sometimes ions will form what are called hydration shells, so they become more ordered in solution. So again, sometimes there are certain ions that when you dissolve them in water, they'll start forming shells of hydration, so these water molecules will order themselves around the cation. And these are small, multiple charged ions, such as aluminum 3+, your transition metals, iron 3+, cobalt 2+, zinc 2+, and therefore the energy of motion is less dispersed. So these small, highly charged ions like +2, +3, transition metals and post-transition metals, when you put them in solution, their entropy is going to be less. It's going to be more ordered. So for your group 1 and some of your group 2 salts, you're going to see an increase in entropy when you dissolve the salt in water. However, for your transition metals, the highly charged transition metals and post-transition metals, when you dissolve those salts in water, you're going to see a decrease in entropy. Your entropy is going to become more negative, which means the system became more ordered. So now let's look here. Sodium chloride, which is a group 1 salt, when it's a solid or liquid phase, solid phase is 72 joules per mole Kelvin. When you put it in solution, it's 115 joules per mole Kelvin, because when you put it in solution, the ions have more freedom of movement, therefore entropy increases. Now we go to aluminum chloride. Aluminum chloride solid is 167 joules per mole Kelvin. But when you put it in water, notice that the entropy drastically decreases. Because again, aluminum chloride is a small, highly charged ion. So again, these are going to be your, +2, +3 charged ions, post-transition and transition metal ions, cations. And you see a significant drop in the entropy because what happens is aluminum 3 plus has these hydration shells where it becomes more ordered. It orders the water around them, so it becomes less disorder and more ordered. Now with methanol, methanol is a polar solute. When you put it in water, you see that there's not much difference. So methanol by itself has a molar entropy of 127. When you put it in water, it slightly increases to 132. And this is because methanol and water have very similar intermolecular forces. So since there are very similar intermolecular forces, there's not going to be much change in the entropy. Because you're replacing water, which has hydrogen bonding, with methanol that has hydrogen bonding. So you're not causing a drastic change in not the structure, but the orientation or what's occurring in the liquid solution. So when you have polar solvents and polar solutes, you really don't see much of a change from liquid to aqueous. So this is for ionic solids. Remember, small multi-charged ions such as Al3 plus, they actually decrease in entropy when you put them in water because they form these spheres of hydration or hydration shells around the cation. And yeah. So with molecular solutes, here we're talking about, polar solutes. There's not much change in the entropy. It's a lot smaller than if you dissolve an ionic compound. And the reason molecular solutes, there's not much change is because there's no separation into ions, no breakdown of the crystal structure, and small alcohols, they have hydrogen bonding. So if you're a solute that has hydrogen bonding, there's going to be really not that much change in the freedom of movement. So methanol, again, since it's a hydrogen bonding small alcohol, there's going to be little change in it. Because again, all you're doing is replacing one type of hydrogen bonding for another type of hydrogen bonding. So like methanol, ethanol, propanol, very little change in the entropy. Maybe a slight increase, but not as much as if you dissolved, say, sodium chloride in water. So as for molecular solutes, generally the change in entropy is much smaller for those compared to your ionic solutes. Now dissolving a gas in a liquid. So here what happens is, gas is very dispersed, has very large freedom of movement. And when you dissolve them in a liquid or a solid, they lose some of that freedom of movement. So the entropy of a solution of gas in a liquid or solid is always less than the entropy of the gas itself. So whenever you dissolve a gas in a liquid, the entropy is going to be less than the gas. So for example, we have O2 gas and we bubble it through water, we get O2 aqueous. So here delta S would be negative because you're taking something that's very dispersed, very disordered, and now you're making it a little bit more ordered. So the entropy is going to be, of the products, is going to be less than the reactants. So therefore delta S would be negative. So whenever you dissolve a gas in a liquid to make a solution, entropy is going to decrease because now you're constraining the movement of the gas molecules. They don't have that dispersed freedom of movement that gases have. So this is what happens when you dissolve a gas in a liquid. So now we're getting into molecular complexity. And so this is within a periodic group. So as we go down a group, as the energy levels become closer together for the heavier atoms, molar entropy increases. So as we go down group 1, you see as we go from lithium to sodium to potassium to rubidium to cesium, the molar mass increases and so does the molar entropy of the solid. Because what happens is as you go from lithium to sodium to potassium to rubidium and cesium, you're adding more energy levels, and as you get higher and higher energy levels, they become closer together. So therefore, the molar entropy increases as you go down a group. The same thing when we have HF, HCl, HBr, and HI, let's say as gases, you see that the molar entropy increases because again there's more energy levels that become closer together. So allotropes, the entropy is higher in the form that allows for more freedom of movement. So for example, we have graphite and diamond. Graphite has more freedom of movement than diamond because diamond is a very rigid three-dimensional structure. So graphite would have a higher molar entropy than diamond. Now if we look at O2 and O3, O3 has more freedom of movement because now these bonds they can stretch and now they can bend. Whereas O2 can only stretch, it can't bend. So O3 would have a higher molar entropy than O2 because it allows for more freedom of motion than compared to O2. So again, graphite and ozone, O3, allow for more freedom of motion, therefore they'll have a higher molar entropy. Again, with molecular complexity, when we're talking about compounds, generally entropy is going to increase with chemical complexity, the number of atoms in the formula, and this is for both ionic and covalent compounds. So typically you can look at the molar mass, and as the molar mass increases, you have more atoms in the compounds, they become more disordered. So for example, tetraphosphorus decaoxide, its molar mass is 281, whereas aluminum chloride, its molar mass is 133. So as you get an increase in molar mass, you have more atoms, therefore there's more chemical complexity, there's more degrees of freedom, the molar entropy increases. That's why tetraphosphorus decaoxide has a greater molar entropy than aluminum chloride or sodium chloride. Now if we look at NO, NO2, and N2O4, here we're adding more atoms and we get more complexity. So there's more degrees of freedom. That's why the molar entropy increases. So you see NO can only stretch. You can only pull that NO atom out and in, out and in. But with NO2, now you have stretching and you have bending of the bonds. So you have more degrees of freedom. And then when you go to N2O4, you have more bending in the molecules. So you have greater disorder, degrees of freedom, so now the energy is more dispersed. And again, the more atoms you have, the greater the molar entropy is. And the heavier it is too. I mean, 14 versus P4O10 has 14 atoms, N2O4 has 6. And you see, even though it's a gas, P4O10 is a lot more, has a higher molar entropy than, oh, excuse me, N2O4 has a lot higher molar entropy than P4O10 because it's a gas. So here we're only comparing apples and apples. So you compare solids with solids, gases with gases. Because when you start intermingling them, it becomes a little bit of a gray area. So again, when we're looking at gases, as you add more atoms to those gases, molecules, more degrees of freedom, molar entropy goes up. Likewise, when we look at solids, as you add more atoms, more degrees of freedom, the molar entropy goes up. So we only compare apples and apples in these comparisons. So here we want to know which of the following would have a negative entropy sign. Select all that applies. So bromine liquid vaporizes. So what does that mean, vaporizes? That means bromine goes from a liquid to a gas. So we have a liquid, excuse me, Br2, my bad, Br2, diatomic. So bromine goes from a liquid to a gas, so the delta S would be, that's right, it'd be positive because we're going from a liquid to a gas, energy is spread out, is dispersed, so entropy increases. Next we have naphthalene sublime. So naphthalene is, let me see, C10. Let me draw it real quick. 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Is C10 H8. And sublimes means it goes from a solid to a gas. So here we're going from a solid to a gas, so you can determine the delta sign, delta S sign would be positive because gases have more entropy than solids. Next, sugar crystals dissolved in water. So we have C6H12O6 solid gives us C6H12O6 aqueous. We're going from a solid to aqueous. Here we can say that the delta S would be positive because again, when an aqueous solution, there'll be a slight increase in it. Iodine vapor condenses into solid iodine. Let's take a look at this one. So we have I2 gas gives us I2 solid. And actually should be sublime. So when we go from a gas to a solid, delta S would be negative because we're localizing the energy. So again, this should be sublime or deposits. Carbon tetrachloride dissolves in benzene. So again, these are both nonpolar compounds. So we got CCl4 liquid, CCl4 aqueous. So we're going to see a slight increase in delta S. So the only one that gives a negative entropy sign in this one is D. That's how you're supposed to, you need to break down all of the processes. So here we want to know which of the following would have a predicted positive delta S. So let's look at them. In the first one, on the reactant side, we have a solid and a gas. On the product side, we just have solid. So since we're going from a solid and a gas to a solid, here we can deduce that the delta S would be negative because we're giving up that solid. In number 2, we have a solid and a liquid, and then we have a aqueous and a gas. And since we have a aqueous and a gas, delta S should be positive because now the energy is more dispersed. Now for number 3, we have 2 moles of gas on the reactant side and 1 mole of gas on the product side. So what happens is our system has compressed. So we're talking about pressure volume. So therefore, since we have fewer moles of gas on the product side than on the reactant side, delta S would be negative. Next, we have H2O gas go to H2O liquid, so we condense steam. Since we're going from a gas to a liquid, delta S would be negative. And then ammonium nitrate would dissolve in water. We get ions, so therefore delta S should be positive. Because those ions are not small, highly charged transition or post-transition metal cations. So the ones that are positive or delta S positive is E and B. Excuse me. So here we want to know the compound that has less molar entropy in it. So in A we have sodium chloride solid, aluminum oxide solid. And the one with lesser entropy in this case, since they're both solids, would be sodium chloride because it has fewer atoms. So that would be the one with lesser molar entropy. Next we have iron 3 chloride solid, iron 3 chloride aqueous. What's the one with less molar entropy? That would be this one, because remember when you put iron 3 chloride in solution, it forms iron 3 plus. It's a small, highly charged transition metal. It's going to be more ordered in solution versus as a solid. Next, we have ethyl cyclobutane and cyclohexane. Since the ethyl cyclobutane has this big long arm here that has freedom of movement, the one with less molar entropy is cyclohexane because it's constrained to that ring. So now, moving on to more of the quantitative part. As we said earlier, the second law of thermodynamics, everything in the universe tends to disorder, randomness, which makes you wonder to think, the universe is cooling down. So since we're cooling down, we're losing disorder. So where is disorder? Fuel for thought. So all real processes occur spontaneously in a direction that increases the entropy of the universe. So for example, a leaf will spontaneously decay once it loses the energy, the life force that keeps a leaf green and alive. So once it loses that energy, that life force, if you want to call it, it decays because everything in the universe tends to disorder. And so the delta S of universe is equal to the delta S of system plus delta S of surroundings. And so if the delta S of universe is greater than 0, it's a spontaneous process. Now the delta S of system is calculated very much the same way we calculated delta H in Jenkin 1. It's the sum of the molar entropies of products minus the molar entropies of reactants. Delta S of surroundings is taking the delta H, dividing it by the temperature, you get delta S of surroundings. So when you add these two together, if it's greater than 0, the reaction is spontaneous at that temperature. If it's less than 0, the reaction is non-spontaneous at that temperature. And if you want to find where it goes from spontaneous to non-spontaneous, you just set delta S to 0 and solve for T in the delta S surrounding equation. So with delta S a system, we use the molar entropies of products and reactants. And so the molar entropies are for different compounds and elements, and it's standard state conditions, which is 1 atmosphere for gases, 1 molar solutions, and pure substance in their most stable forms for solids or liquids. Now for enthalpy, if you remember, there were certain ones that had 0 heats of formation. Those were elements in their pure state. Because for enthalpy, there's no 0 point to measure from. So we can only measure changes, and that's why the elements in their pure form were set to 0, and then we can measure the change when they are involved in reactions or processes. Now with entropy, we do have a 0 point. And we can determine the absolute values by applying the third law of thermodynamics, which says a perfect crystal has 0 entropy at 0, absolute 0, which is 0 Kelvin. So at 0 Kelvin, there is no disorder. Now this is important because now since we have this, what does this mean? This means everything, elements, even in their pure form, have a molar entropy associated with it, because now we have a 0 point. Secondly is the coldest we can get is by blowing liquid helium, and I think we get around 4 or 2 Kelvin is the coldest that is we have reached, as far as I know. So this is important again because now everything has a molar entropy, even elements in their pure stable states. This is just showing you. So you have a entropy curve, much like a heating curve. So as you increase the temperature, the solid melts. When it goes from a solid to a liquid, this is the entropy of fusion. So you see a big jump in the entropy, no change in temperature. Then you start heating, entropy increases until you get to the boiling point. Then there's a big jump. You go to entropy of vaporization, and then entropy continues to increase. And at different temperatures, you have different molar entropies. So now, given the following equation, calculate the delta S universe at 450 Kelvin. So it gives us the delta H of reaction for this combustion reaction. Calculate delta S of universe, which is this delta S of system plus delta S of surroundings. And so first we need to calculate delta S of reaction. Which equals, the molar entropy of products minus reactants. So we have 3 times the molar entropy of CO2 plus 4 times the molar entropy of H2O gas. And make sure you use the gas because liquid, gas, and solid all have different ones. Minus, now the reactants, we have 1 times the molar entropy of propane plus 5 times the molar entropy of O2. So that becomes delta S of reaction equals 3 times, what's the molar entropy of CO2? 213.8 plus 4 times the molar entropy of H2O gas, 188.8 minus propane, 270.3 plus 5 times O2, 205. 0.2. Now, before we continue, let's predict the sign of delta S. So on the reactant side, we have 6 moles of gas. On the product side, we have 7 moles of gas. So we can predict that delta S should be positive because we increased the moles of gas. So when we calculate the delta S of reaction, hopefully, if our prediction is correct, we should get a positive delta S. $1,400 minus $13. Let me do this better. $12.96. Do the other one again. 3 times 213. $13.97. So here you see that delta S of reaction is in fact positive. 101. Positive 101 joule per mole. Oopsie doopsie. All right, so that's delta S of reaction. Now delta S of surroundings equals negative, the delta H of negative 244 divided by T, and T in this case is 450 Kelvin. 4.54 kilojoules per mole Kelvin. So obviously we need to either convert delta S of surroundings into joules or delta S of reaction into kilojoules, and that's what I'm going to do. So delta S of reaction equals 0.101 kilojoules per mole Kelvin. So delta S of universe equals 4.64 kilojoules per mole. Now, since delta S of reaction and delta S of surroundings are positive, this reaction is always spontaneous at all temperatures. So there's not a temperature where it's going to be negative because Kelvin is always a positive temperature. Alrighty. So now we're going to get into another thermodynamic property called Gibbs free energy, or simply we just call it free energy or delta G, and it's a combination of the system's enthalpy and entropy. So the difference between the enthalpy and entropy of a system gives us G, or if we measure the change, it gives us delta G, which is a measure of its spontaneity. And this is actually very useful for us. So for delta G of a system, it equals delta H of system minus T delta S of system. And we know how to calculate delta H of system and the delta S of system. And so when delta G is less than 0, it's spontaneous. When delta G is greater than 0, it's non-spontaneous. And if you want to look for where it goes from spontaneous to non-spontaneous, you just set delta G equal to 0 and you solve for T. And so this table is very important to understand. So if you have an exothermic reaction and it increases in entropy, it's always spontaneous at every temperature. Now, if you have an endothermic reaction that is less disorder, so negative delta S, then it's always going to be non-spontaneous because two negatives make a positive, and therefore delta G will never be a negative. So those two are the two extremes. Now the other two is where you have a cross from spontaneous and non-spontaneous to spontaneous. So if you have an endothermic reaction which increases in disorder, so delta S is positive, it's spontaneous at high temperature and non-spontaneous at low temperature. So you can actually set delta G to 0 and solve for T and determine the temperature at which it goes from non-spontaneous to spontaneous, because it's going to be a high temperature. Now, if it's exothermic and it decreases in disorder, well, then it's going to be spontaneous at a low temperature and non-spontaneous at a high temperature. And so again, you can set delta G equal to 0 and see where it crosses from spontaneous to non-spontaneous. Again, the temperature that it's going to give you is going to be in Kelvin. So make sure you review over this chart and understand how the different signs of delta H and delta S change the sign of delta G. So here we have a reaction, and we wanted to determine when does this reaction go from non-spontaneous to spontaneous? And you see that we have 3 moles of gas on the reactant side, 2 moles of gas on the product side. So we can deduce that the delta S of reaction should be negative because we're decreasing the moles of gas. So first we calculate the delta H of reaction, products minus reactants. Again, Cl2 is in its pure element in its natural stable state, gas, so there's no heat of formation for it. So delta S of reaction is exothermic. Delta S of reaction is negative, just like we predicted. So we have a negative delta H and a negative delta S. And remember that delta G equals delta H minus T delta S. And so what does this tell us is if delta S is negative, that means at low temperature, it's going to be spontaneous. At high temperature, it becomes non-spontaneous. So now what we do is we set delta G of reaction equal to 0 to see when is the temperature going to go, when is it going to cross from spontaneous to non-spontaneous. Again, Since delta H is negative, delta S is negative, at low temperature, it's going to be spontaneous. At high temperature, it's going to be non-spontaneous. So what we do is we set delta G equal to 0 and solve for T. Please note that for delta S, I converted it to kilojoules before putting it into that equation. So we solve for T, we get T to be 637 Kelvin. Please note that T should always be positive. If you get a T that's negative, either you did something wrong, or that also tells you that it can never be spontaneous or non-spontaneous. And so it goes from spontaneous to non-spontaneous when you hit 364 degrees Celsius. So below 364 degrees Celsius is spontaneous. After 364 degrees Celsius, it becomes non-spontaneous. So now we want to look at this reaction and determine whether it's going to be spontaneous or non-spontaneous. Or is it a mix of the two? All right, so I've given you a few minutes to look at it. So two things we should look at here. First off, heat is a reactant, so that tells us delta H is positive because it's an endothermic reaction. Secondly, we go from a liquid to get 3 moles of gas on the product side. So this tells us delta S is positive as well. So now we look at our equation. Delta G equals delta H minus T delta S. So if we look at this, we see that delta H is positive and delta S is positive. So this reaction is going to be non-spontaneous at low temperatures because delta H is positive, and spontaneous at high temperatures because delta S is positive as well. So delta H is positive and delta S is positive. So when the temperature, the magnitude of the temperature overcomes delta H, then T delta S is going to be negative, and that means it's going to be spontaneous. So it's going to be spontaneous at high temperatures. So it would be B. Spontaneous at high temperatures. It's going to be non-spontaneous at low temperature. So that's one way we can calculate delta G, is determine the delta H of reaction, the delta S of reaction, get the difference. Another way is to use standard free energy change, which is delta G naught when the components are in the system or in their standard states. And again, standard states is 25 degrees Celsius, 1 atm, 1 molar solution. And so we get these delta G naught, which means it's at standard conditions. The naught means it's at 25 degrees Celsius, 1 atm, 1 molar solutions. And so if you're calculating delta G naught, there's actually two ways to calculate it. Again, this is only when it's at 25 degrees Celsius. If it's at any other temperature, you have to use delta G equals delta H minus T delta S. But when it's the naught, it means it's at their standard states, which is 25 degrees Celsius, 1 atm, 1 molar solution. So again, the naught, 25 degrees Celsius. So if you're wanting to calculate the free energy change at 25 degrees Celsius, there's two ways to do it. The first way is the way we just showed you, delta H minus T delta S. The second way is using what's called Gibbs free energy of formation values. So we take the Gibbs free energy of formation of products minus the delta G of formation of reactants. That gives us the delta G naught of the reaction. Again, this can only be used if you're at 25 degrees Celsius. And so this is another table in the thermodynamic table in the back of your book. The delta GF of nulls are similar to delta HF of nulls. And so if an element is in their standard state, the delta G of formation is 0, just like with delta H. And of course, you multiply the coefficient by the Gibbs free energy of formation for that reactant or product. And if you, just like delta H, if one way is spontaneous, the reverse way is going to be non-spontaneous. So these are tabulated values in the back of the book. For pure elements, the Gibbs free energy of formation is 0. You can use at 25 degrees Celsius, you can use either way, and it's going to give you roughly the same answer. Now, if it's not at 25 degrees Celsius, you have to use delta G equals delta H minus T delta S. So we're going to calculate the delta G of this reaction using delta H and delta S, and it's going to be at 298 Kelvin. So let's do that. So we find delta H, we find delta S, we find that delta G of reaction is negative 41 kilojoules. Again, you got to convert delta S into kilojoules. So that's using this way, the delta H minus T delta S to calculate delta G of reaction. Products minus reactants, multiply the formation, heats of formation by their coefficients, and the Gibbs free energy formation by their coefficients. So delta G naught is negative 41 kilojoules per mole. Now, if we use the Gibbs free energy of formation values to calculate delta G naught at 298 Kelvin, again, the same reaction. We look up in the back of the book, we get the Gibbs free energy of formation values. We do products minus reactants, and you see we also get negative 41.06 kilojoules per mole. So either way you can use when you're at 25 degrees Celsius. If you're not at 25 degrees Celsius, you have to use delta G equals delta H minus T delta S. So now we're going to see how Gibbs free energy change is related to equilibrium constant, and that's this equation here. Now there's going to be a lot of equations in this chapter. Don't worry, you just have to know how to use the equations. The equations will be provided for you on a test. So delta G naught equals negative RT ln of K. And R equals 8.314 joule per mole Kelvin. Now the naught means it's at temperatures at 298 Kelvin. If there's no naughts, it could be at some other temperature. So if K is greater than 1, then the ln of K is greater than 1, and then delta G is going to be less than 0. So when your K is very large, it's going to be spontaneous, which makes sense. Now if your K is less than 1, then ln of K is going to be negative, so delta G is going to be positive, non-spontaneous. It's going to go in the reverse direction, which makes sense. Small k means it's going to be mostly reactants, very few products, so it's not going to be very spontaneous. If k equals 1, then ln of k equals 0. The reaction is at equilibrium. So here we want to use the appendix, and I've got the delta G of formation values. We want to determine the K at 298 for the synthesis of carbon monoxide. So the first thing we're going to do, determine the delta G of reaction. So 2 times the Gibbs free energy of formation of CO gives us negative 274.4. So this is a spontaneous reaction at 298. So the K should be very large. Now to solve for K, we rearrange this equation, and remember the inverse of ln is E. So we move everything to the other side, we get delta G naught over negative RT equals ln of K. So K equals E raised to the negative delta G naught over RT. We solve this, we get the K of the reaction. 1.26 times 10 to the 46. This means it's a very spontaneous reaction. Doesn't mean it's instantaneous, it means it's spontaneous at 298 Kelvin. Now, here we want to calculate the delta G given the K for this reaction. So we have this reaction involving hydrogen chloride gas plus bromine liquid gives us hydrogen bromide gas plus Cl2 gas. And the K is very small at 298 Kelvin. It's 2.22 times 10 to the negative 15. So when you look at this K, the K is very small. That means delta G is going to be positive because it's going to be non-spontaneous. So we set up the equation. We put in our R and T, the ln of 2.2 times the negative 15. We get delta G is 83.6 kilojoules per mole. That's, since it's positive, it's non-spontaneous at 298 Kelvin. And this is how you can use K to find delta G and also use delta G to find K. So this is just showing you the magnitude of delta G when you see the magnitude of K. When K is very small, delta G is very large, almost 200 kilojoules. You decrease the exponent by half. You see we decrease the delta G by half. It becomes, less. We decrease the K by another half. Delta G decreases the by half. So as we decrease the exponent by a half, we see that the delta G decreases by the same amount. So we get, 5 to the first, negative 10, 6 to the 8th, 10 to the 8th is negative 50, of course 10 to the 35th, negative 200. So again, the bigger the K value means it goes in the forward reaction almost to completion. If it's a very small K value, it means its reverse reaction goes almost to completion. So make sure you familiarize yourself with this table. Now, we can also find free energy change under any conditions. Remember, delta G naught is when we're at standard conditions, which is 1 molar, 1 atmosphere, and 25 degrees Celsius. But let's say we're not at standard conditions. We're at some other conditions. This is the equation we use to find delta G. So we take the delta G naught plus RT ln of Q. And if you remember from the chapter on kinetics, Q is products over reactants. Or equilibrium, I'm sorry. Equilibrium is products over reactants. And so here we have this delta G, this reaction. We give them the delta G naught. We want to calculate K at 298 and also calculate delta G when the concentrations of reactants and products are not standard conditions. So they're not 1 molar concentrations. So again, Q is just like the Q we learned about when we talked about equilibrium. The coefficients become the exponents of the products and reactants. Remember that Q is products over reactants. So to calculate K, all we need to do is use delta G and rearrange that. Delta G equals negative RT ln of K, and we solve for K. So K is very large because delta G naught is negative. So it's a spontaneous reaction. No surprise there. Now let's calculate delta G at these non-standard conditions. So we have the delta G naught. We convert that to joules because R is also given in joules. So since R is given in joules, I converted delta G into joules. Have to be the same unit. And then remember it's products, the 1.5 over reactants, 0.5 times 0.2. And then we just solve for delta G. And we see that the spontaneity decreased a little bit because as you notice, we have more We have a mixture of products and reactants, so it's not going to be as spontaneous as if we had no products. We have a mixture of products and reactants, so the spontaneity decreases. And so this is how you find delta G at non-standard state conditions. Again, you don't have to memorize the equations. They will be provided for you. You just have to know how to utilize the equations. So that concludes entirety of chapter 20. Again, the main things are entropy. Can you calculate delta S of universe, determine if something is spontaneous or non-spontaneous? If it's non-spontaneous or spontaneous, is there a temperature at which it crosses between the two? Also, can you look at a chemical reaction and predict the sign of delta S? Or given different types of compounds or elements, can you predict the sign of delta S as well? For Gibbs free energy, can you calculate delta G either using one of the two methods we talked about? Can you, based on the sign of delta H and delta S, predict the sign of delta G? Can you use delta G to find equilibrium constant or equilibrium constant to find delta G? And lastly, can you find delta G at non-standard state conditions? So these are the main things that you should focus on in this chapter. So on that note, that's all I have for this session. I hope you enjoyed it. If you did enjoy it or you learned something new, make sure you hit the like button. Leave a comment if you like. And until next time, it's Dr. Armand signing off.